Welcome to these gentle, soothing stories for sleep. I'm so glad you are here. Whether you are preparing to drift off to sleep, relaxing after a long day, or simply seeking a quiet companion for your thoughts, you have found a soft place to land. Tonight, we will begin a journey together. A quiet contemplation of one of the most profound questions imaginable. Exploring not with fear, but with a gentle curiosity. Our story is called The Last Whisper of Starlight. Could the universe ever come to an end? Before we begin, I would love to know where you are listening from tonight, or perhaps how your day was. Please feel free to leave a comment below. Wherever you are in the world, I hope you are feeling comfortable, relaxed, and ready to explore something gentle yet extraordinary. And if you find these soothing scientific journeys bring you a sense of peace or wonder, please consider liking this video and subscribing to the channel. It helps more souls who are searching for quietude to find their way here. Imagine, if you will, the deep and calming silence that settles upon the world after the last crackle of a campfire. You are sitting there in the cool of the evening, wrapped in a warm blanket, watching the final moments of a fire that had danced and roared with such life only hours before. The vibrant, leaping flames have long since retreated, and now all that remains is a soft, pulsating bed of embers, glowing like a miniature, sleeping galaxy in the heart of the darkness. You can feel the warmth on your face beginning to fade, replaced by the gentle chill of the night air, which carries the faint, nostalgic scent of wood smoke. Each ember is a tiny sun, a world of deep orange and crimson, and you watch as, one by one, they surrender their light, a slow and graceful sigh into the encroaching shadows. A faint breeze whispers through the trees, stirring the grey ash, and the final points of light wink out, leaving behind only a profound stillness and the memory of warmth. This quiet, gentle ending is something we understand almost instinctively, a natural and peaceful transition from energy to quiet, from light to dark, a rhythm as old as the world itself. It feels not like a destruction, but like a completion, a final, soft exhalation. This beautiful, simple process of a fire slowly burning itself out is a perfect, small reflection of one of the most fundamental and powerful laws of our entire universe. This principle is known as entropy, and it is governed by a rule called the second law of thermodynamics. It sounds complex, but at its heart, it is as simple and as intuitive as the dying fire before us. The law essentially states that in any closed system, things have a natural tendency to move from a state of order to a state of disorder. The log that you placed on the fire was a highly ordered structure. Its wood fibers contained complex molecules, holding a vast amount of concentrated, potential energy. When it burned, that order was broken down. The energy was released as light and heat, which did not vanish, but instead spread out, dissipating into the vastness of the night sky. The log's complex molecules were transformed into simpler, more chaotic things. Fine particles of ash, plumes of smoke, and invisible gases that drifted away on the wind. The system, which was once neat and concentrated, became messy and spread out. Entropy, you see, is simply a measure of this disorder, and the second law tells us that this measure, in our universe, always tends to increase. It is the reason a hot cup of coffee will always cool down to room temperature, its heat spreading into the cooler air around it, but you will never see a lukewarm cup spontaneously gather heat from the air to become hot again. It is the reason that if you shuffle a new, ordered deck of cards, it is almost impossibly unlikely that you will ever shuffle them back into their original, perfect sequence. The universe, it seems, has a one-way street, an arrow of time that always points from order towards disorder, from the neatly stacked log to the scattered ash. This relentless march towards equilibrium, towards a state where energy is perfectly and evenly spread out, is the silent, underlying rhythm to which all things in the cosmos must eventually dance. It is the universe's own slow, deep breath, inhaling order and exhaling a gentle, ever-expanding chaos. And in this process, we find not an aggressive destruction, but a universal settling, a gradual return to a state of profound peace and simplicity. The energy of the fire is not lost, it has simply changed its address, becoming a part of the greater whole, its warmth now an indistinguishable part of the vast, cool night. All endings, it seems, from the smallest ember to the grandest cosmic scales, are not true annihilations, but beautiful and profound transformations. A rearranging of the universe's furniture, that small, fading fire, with its final, whispered glow, is a perfect miniature of a much, much grander fire in our sky, the one that bathes our world in light and makes all of our life possible. And as we watch its last embers fade, we might find ourselves wondering, does our own sun, in its magnificent celestial hearth, also have its own final embers? Picture the most beautiful sunset you have ever seen, that fleeting, magical moment when the world is held in a perfect, quiet balance between day and night. The sky is a vast canvas, painted in impossible hues of soft orange, deep rose, and ethereal violet. Now, imagine that single, perfect moment of sunset stretching out, lasting not for a few minutes, but for 1,000,000 years. This is the beginning of the long, slow sunset of our own star, the sun. It is a future so distant it feels like a dream, yet it is a destiny written into the very fabric of physics. In this far-flung future, we could imagine standing on a world looking up at a sky dominated by a sun that has begun its final, magnificent act. The light it casts is no longer the familiar, friendly yellow-white, but a deep, burnished, crimson glow, and the warmth it provides has grown into an overwhelming, pervasive heat. The oceans of this world would have long since begun to steam, their surfaces shimmering and misting into a thick, humid atmosphere that veils the stars. The world itself would be quiet, not the silence of peace, but the silence of exhaustion, of a planet basking in the final, all-consuming warmth of its parent stars long goodbye. This is not a sudden and violent end, but a gradual, majestic, and achingly slow transformation. A final, beautiful exhalation of light that will unfold over a timescale we can barely comprehend. The story of our sun, and indeed of all stars like it, is a grand and elegant drama of balance. For most of its life, for the nearly 5 billion years it has already existed, and for the 5 billion more it has left, the sun is in a state of perfect equilibrium. Deep within its core, the temperatures and pressures are so immense that they create a natural furnace, a celestial engine of unimaginable power. Here, the simplest and most abundant element, hydrogen, is being subjected to such an intense gravitational squeeze that its atoms are forced to fuse together, creating the next heaviest element, helium. This process, known as nuclear fusion, releases a colossal amount of energy in the form of light and heat. This outward-pushing energy from fusion is constantly fighting a battle against the relentless inward pull of the sun's own immense gravity. For billions of years, these two titanic forces are perfectly matched. Gravity tries to crush the star into a tiny point, while the nuclear furnace at its core pushes back with equal force, creating the stable, life-giving star we know and love. But this perfect balance cannot last forever, because the hydrogen fuel that powers the furnace is finite. When the sun has been burning for about 10 billion years, the hydrogen in its core will begin to run out. With less fuel for fusion, the outward push will weaken, and gravity will begin to win the battle. The core of the sun will start to contract and, paradoxically, as it gets squeezed, it will get even hotter. This intense new heat from the collapsing core will cause the sun's outer layers, which still contain plenty of hydrogen, to begin fusing at a much more furious rate. This new, supercharged fusion will produce so much energy that it will cause the sun's outer layers to swell outwards, expanding to an enormous size. The sun will transform into what astronomers call a red giant. It will become so large that its fiery edges will expand past the orbit of Mercury, past Venus, and possibly even engulf our own Earth, turning our blue marble into a charred, molten cinder. As its surface expands, it will also cool, which is why its color will shift from brilliant yellow-white to a deep, ominous red. After perhaps 1 billion years as a red giant, the sun will enter the final, most gentle stage of its existence. The helium in its now incredibly hot core will itself begin to fuse into heavier elements like carbon and oxygen. Eventually, this fuel will also be exhausted, and with no more energy being generated, the sun's outer layers will drift away into space in a series of gentle puffs, creating a vast, beautiful, and intricate cloud of glowing gas known as a planetary nebula. These ethereal structures, with names like the Ring Nebula or the Helix Nebula, are the ghosts of dead stars, their constituent elements sent back into the cosmos. And at the center of this beautiful, expanding shroud of gas, all that will be left of our magnificent sun will be its tiny, incredibly dense, cooling core. This remnant, about the size of the Earth but containing half the sun's original mass, is called a white dwarf. It will be a smouldering stellar ember, no longer producing new heat, that will simply spend trillions of years slowly radiating away its leftover warmth, eventually fading into a cold, dark object known as a black dwarf, lost in the eternal darkness of space. This quiet, graceful fade into the night is the destiny of our star, a destiny so far in the future it is almost meaningless on our human scale, yet it provides a profound and humbling perspective on our own fleeting, precious moment of warmth and light. Our sun's ending is a quiet fade, a gentle sigh. But some stars, the true titans of the cosmos, the ones born many times more massive than our own, choose to leave the stage not with a whisper, but with a final, thunderous roar. Have you ever sat in a quiet moment and considered the simple, profound fact that the iron in your blood, the very element that carries oxygen through your veins and gives you life, was forged in the heart of a colossal, dying star billions of years ago? Or that the calcium that gives strength to your bones, the potassium that helps your nerves to fire, were created in a celestial furnace so violent it would make our own sun look like a gentle candle? We are, in the most literal and poetic sense, the children of the stars. Our bodies are walking, breathing museums of cosmic history, assembled from the ashes of suns that lived and died long before our Earth was even a whisper of dust and gas. To understand this is to touch a truth that connects us to the grandest cycles of the cosmos, to see that even the most spectacular and violent of endings are not just destructions, but acts of breathtaking creation. To understand our own existence, we must first travel back in time and space, into the core of a star born to die a glorious death. Imagine a star many times more massive than our sun, a true titan of the galaxy, a brilliant blue-white giant burning through its fuel at a ferocious rate. Inside its core, the pressures and temperatures are beyond anything we can truly imagine. It is an elemental forge where gravity is the hammer and heat is the flame. Just like our sun, it begins by fusing hydrogen into helium. But because of its immense mass, and therefore its much stronger gravity, its core becomes far hotter and denser. Once the hydrogen is gone, it has enough gravitational power to begin fusing the leftover helium into carbon. And then, in a series of nested shells, like the layers of a cosmic onion, it continues this alchemical process, fusing carbon into neon, neon into oxygen, oxygen into silicon, and finally, after millions of years of this furious stellar blacksmithing, it creates iron. Here, in the heart of the star, the journey of creation comes to a sudden and dramatic halt. For all the elements leading up to iron, the process of fusion releases energy, the very energy that pushes back against gravity and keeps the star alive. But iron is different. Iron is the most stable atomic nucleus. To fuse iron into something heavier does not release energy. It consumes it. Iron is stellar ash. It is the end of the line. When a massive star builds up a core of iron, it has written its own death warrant, and the end comes with astonishing speed. With no more energy being produced by fusion to counteract the pull of gravity, the star's core collapses in on itself. In less than a second, a ball of iron the size of the Earth is crushed by gravity into a super-dense object, only a few dozen kilometers across. This catastrophic collapse is so violent that the core particles are squeezed together, and then they rebound, creating a titanic shockwave that blasts outwards through the star's outer layers. This is a supernova, an explosion so luminous it can briefly outshine its entire host galaxy, a single star releasing more energy in a few moments than our sun will in its entire 10 billion year lifetime. It is in the unimaginable crucible of this explosion that the universe's greatest act of alchemy takes place. The sheer energy of the shockwave provides the necessary force to fuse elements heavier than iron, creating all the precious and rare materials we know. Every atom of gold in a wedding ring, every bit of silver in a photograph, every trace of uranium that powers a nuclear reactor was created in the final, dying scream of a massive star. This stellar detonation then blasts all of these newly forged elements, from the lightest hydrogen to the heaviest uranium, far out into interstellar space, enriching the gas and dust clouds of the galaxy. It is from these very clouds, seeded with the remnants of a previous generation of stars, that new solar systems are born. A cloud of gas and supernova debris collapses under its own gravity to form a new star, and the leftover material forms a swirling disk that will eventually coalesce into planets, moons, and asteroids. Our own solar system is a third-generation system, meaning the material that makes up our planet, our sun, and our own bodies has been through this cycle of stellar birth, death, and rebirth at least twice before. The spectacular death of one star is the necessary precondition for the birth of another, and for the emergence of planets rich enough in heavy elements to support life. These stellar endings happen within vast, breathtaking collections of stars, cosmic islands that drift in the great, dark ocean of space. We call them galaxies. But what holds these cosmic islands together? And could they, too, fall apart? It feels as though we are standing on solid ground, a firm and unmoving foundation in a quiet corner of the universe. But this feeling is a profound illusion. Right now, at this very moment, you and I, and our entire planet Earth, are hurtling through space at a speed of about 80,000 kilometers per hour as we orbit the Sun. And that is only our local motion. Our entire solar system, our Sun and all its planets, is being carried along in a grand, sweeping arc as it orbits the center of our Milky Way galaxy. That journey is happening at a staggering 800,000 kilometers per hour. We are riding on a vast celestial carousel, a spinning disk of over 200 billion stars, so large that it takes our Sun about 230 million years to complete a single rotation. And yet, we feel nothing. We are held in place, not by a physical restraint, but by an invisible, silent, and all-pervasive influence that reaches across the cosmos. To understand it, we must imagine a vast, unseen web, an invisible architecture stretching through the voids between the stars and the galaxies, its threads guiding the graceful dance of cosmic structures, its immense weight bending the very fabric of reality itself. For centuries, we understood this influence as gravity, a force, an invisible rope pulling objects toward one another, as described by Isaac Newton. But in the early 20th century, Albert Einstein gave us a revolutionary new way to see it. In his theory of general relativity, gravity is not a force at all. It is the consequence of mass and energy warping or curving the four-dimensional fabric of our universe, a fabric he called space-time. The classic analogy is to imagine a stretched-out rubber sheet. If you place a heavy bowling ball in the center, the sheet will bend and sag. That is what a massive object like the Sun does to space-time. And if you then roll a smaller marble nearby, it will not travel in a straight line. Its path will be deflected by the curve in the sheet, causing it to circle the bowling ball. That is what a planet like the Earth does as it orbits the Sun. It is simply following the straightest possible path through a curved reality. Mass tells space-time how to curve, and the curvature of space-time tells matter how to move. This beautiful and elegant theory perfectly describes how our planets orbit the Sun and how stars are held within their galaxies. Or, at least, it almost does. In the 1970s, astronomers studying the rotation of distant galaxies noticed something deeply strange. According to Einstein's and Newton's theories, the stars on the outer edges of a spinning galaxy should be moving much more slowly than the stars closer to the center, just as the outer planets in our solar system move more slowly than the inner ones. But what they found was that the outer stars were moving just as fast, if not faster, than the inner stars. The galaxies were spinning so rapidly that the gravity from all the visible matter, all the stars, gas, and dust we could see, was not nearly enough to hold them together. They should have flown apart, flinging their stars into the intergalactic void. There had to be something else there, an enormous amount of unseen mass providing the extra gravitational glue needed to keep these galaxies intact. This mysterious, invisible substance was given the name dark matter. We call it dark not because it is black, but because it does not seem to interact with light or any other form of electromagnetic radiation. It does not shine, it does not reflect, it does not absorb. It is, for all intents and purposes, completely invisible to all of our telescopes. We cannot see it, we cannot touch it, but we can watch its profound gravitational effects on the things we can see. It is the unseen weaver in the cosmic tapestry. Subsequent observations have confirmed that dark matter is not just a minor anomaly. It is a fundamental component of our universe. All the normal matter that we are familiar with, the stuff that makes up stars, planets, and ourselves, accounts for only about 5% of the total mass and energy content of the universe. Dark matter, this invisible scaffolding upon which galaxies are built, is thought to make up a staggering 27%. The vast majority of our universe is utterly hidden from us, a silent, invisible presence that dictates the structure and the fate of everything we hold dear. We are living in a cosmos whose true nature is overwhelmingly unknown, a profound mystery that reminds us of the humility we must have when we look up at the night sky. We are just beginning to perceive the true scale of the forces at play. And so we must ask, if an unseen gravity is working so tirelessly to hold the universe together, is there also an unseen force, something even more mysterious, that is working just as hard to pull it all apart? Listen closely. In the deepest quiet of the night, if you still your mind and focus on the profound silence between sounds, can you hear it? It is not a noise that travels through the air to your ears, but a deep, fundamental vibration of existence itself. It is the sound of the universe getting bigger, the whisper of space-time stretching into an ever-expanding silence. We are all adrift on a current we cannot feel, a river of cosmic expansion that is carrying everything away from everything else. To grasp this incredible reality, imagine we are in a warm, cosmic kitchen, watching a loaf of raisin bread bake in an oven. Before it goes in, the dough is small and dense, and all the raisins are relatively close together. But as the loaf bakes, the dough begins to rise and expand, pushing all the raisins further apart from each other. Now, it is crucial to see that the raisins are not moving through the dough on their own. They are stationary within the dough, but the very fabric of the dough itself is swelling and stretching, carrying them along for the ride. From the perspective of any single raisin, it would look as though all the other raisins are moving away from it. And the further away a raisin is, the more dough there is between them to expand, and so the faster that distant raisin would appear to be moving away. This is precisely what we see when we look out into the universe. In the 1920s, the astronomer Edwin Hubble made one of the most monumental discoveries in human history. While observing distant galaxies, he noticed that their light was stretched out towards the red end of the spectrum, a phenomenon known as redshift. This is similar to how the pitch of an ambulance siren drops as it moves away from you. This redshift told him that these distant galaxies were all moving away from us. More than that, he found a clear relationship. The farther away a galaxy was, the faster it was receding from us, just like the raisins in our expanding loaf of bread. This was the first concrete evidence that our universe was not a static, unchanging stage, but a dynamic, evolving entity that was growing larger with every passing moment. The universe is expanding. And just like with the raisin bread, this isn't an explosion from a single central point into a pre-existing emptiness. The very fabric of space-time itself is stretching everywhere at once. Every kilometer of space is becoming a little bit bigger every second, carrying the galaxies, the great cosmic islands of stars, along with it. For most of the 20th century, cosmologists assumed that this expansion must be slowing down. After all, the universe is filled with matter, and the collective gravity of all this matter should be acting like a brake, gently tugging on the expansion and perhaps, one day, even halting it or reversing it. It seemed like the only logical outcome. But the universe, it turns out, is far stranger than we ever imagined. In the late 1990s, two independent teams of astronomers were studying distant supernovae to measure the rate of this cosmic slowdown. What they found was so shocking, it was initially thought to be an error. The expansion of the universe was not slowing down. It was speeding up. Something was working against gravity. Something was pushing the universe apart at an ever-increasing rate. This mysterious, repulsive influence was given a name as enigmatic as its nature: dark energy. Unlike dark matter, which clumps together gravitationally, dark energy seems to be a smooth, uniform property of space itself. It is an intrinsic energy of the vacuum, a kind of anti-gravity that pushes instead of pulls. And according to our best understanding, as the universe expands and more empty space is created, more dark energy comes into existence along with it. This creates a powerful feedback loop. The expansion creates more space. The new space contains more dark energy, and the new dark energy pushes space-time to expand even faster. This accelerating expansion paints a picture of a very strange and lonely future. As the eons pass, distant galaxies will be pushed away from us faster and faster. Eventually, they will recede from us so quickly that they will cross a cosmic horizon, a point of no return, beyond which their light, even traveling at the maximum speed possible, will never be able to reach us again. One by one, the familiar galaxies will wink out of our night sky, their light red-shifted into oblivion. Our cosmic view will slowly diminish, until our own local group of gravitationally bound galaxies is all that remains. A single, isolated island in an endless, empty, and eternally darkening ocean. This cosmic stage is now set for a final, epic tug-of-war. On one side, there is gravity, amplified by dark matter, working to pull everything together. On the other side, there is dark energy, pushing everything apart. The ultimate winner of this cosmic battle will decide, once and for all, how the story of the universe comes to an end. So what might it look like, in the unimaginable future, if dark energy wins a complete and overwhelming victory? Imagine you are holding a favorite old sweater, a garment woven from countless threads that has brought you comfort and warmth for years. You notice a single, tiny, loose thread, just a small loop. At first, it is nothing. But if you were to take that thread and pull it, gently but persistently, you would see the very fabric of the sweater begin to change. The weave would stretch, the patterns would distort, and if you continued to pull, the entire garment would begin to slowly, quietly, and completely unravel into a cascade of individual threads. This gentle, inevitable dissolution, this quiet coming apart at the seams, is perhaps the best way to imagine one of the most dramatic, yet strangely serene, possible fates for our universe. A scenario known to cosmologists as the Big Rip. It is an ending not of fire or ice, but of a slow, inexorable, and ultimate unraveling of the very fabric of reality itself. To contemplate it, we must feel that same gentle, persistent pulling, not on a thread of wool, but on the threads of space-time that bind all things together, from the mightiest galaxies down to the smallest particles in the palm of your hand. The Big Rip is a speculative, but physically plausible hypothesis about what could happen if the dark energy driving the universe's acceleration is even more powerful than we currently think. This theoretical, superpotent form of dark energy is sometimes called phantom energy, and its defining characteristic is that its density would increase over time. As the universe expands, the amount of phantom energy in each patch of space would grow, making its repulsive force stronger and stronger until it would eventually become powerful enough to overcome all the other fundamental forces that hold the universe together. This would not happen all at once, but in a series of distinct, final stages, a cosmic unraveling on progressively smaller and smaller scales. According to the models, the first structures to be affected would be the largest ones, those held together by the weakest gravitational bonds. In a future, perhaps tens of billions of years from now, the repulsive force of dark energy would become strong enough to tear apart the great superclusters of galaxies. A few billion years later, it would overcome the gravity holding individual galaxies together, and the Milky Way itself would be torn asunder, its billions of stars flung into the expanding darkness. Then, as the end drew nearer, the unraveling would accelerate. A few months before the final moment, the gravitational grip of stars on their planets would fail, and solar systems like our own would be dismantled. The Earth, if it still existed, would be cast loose, a rogue planet wandering into the void. In the final minutes, the process would become catastrophically swift. The stars and planets themselves, no longer able to hold their own forms together against the overwhelming expansion, would be ripped apart. And then, in the last fleeting fractions of a second, the fundamental forces that operate on the microscopic scale would be defeated. The electromagnetic force, the glue that binds atoms together, would give way, and every atom in the universe would be pulled apart into its constituent electrons and nuclei. Finally, in the very last instant, the strong nuclear force, the most powerful force in nature, the one that holds atomic nuclei together, would also be overcome. Every proton and every neutron would be torn apart into a spray of quarks and gluons. The universe would be reduced to a soup of fundamental particles, each one utterly isolated from every other, with the space between them expanding infinitely and instantaneously. The very notion of distance and separation would lose its meaning. The fabric of space-time itself would be torn. This is an end of total and complete dissolution. But this terrifying vision, this cosmic tear, is just one possibility, one outcome of the cosmic battle where the outward push is all-powerful. It is predicated on a specific kind of dark energy that may or may not exist. But what if the balance of power were different? What if, in the eons to come, gravity and dark matter held their own? Or what if, for some reason we do not yet understand, dark energy were to weaken and fade? What if the expansion of the universe were to slow, to stop, and then to reverse? Every breath you take is a quiet, unconscious cycle of expansion and contraction. Your chest rises, your lungs fill with air, and for a moment you are full of the world. Then, just as gently, you exhale, releasing what you have taken in, your body contracting in a soft, rhythmic return. This simple, life-sustaining act of breathing is a perfect mirror of a grand cosmic possibility, a theory that envisions the entire universe as a single, colossal organism taking one unimaginably long breath over hundreds of billions of years. We have just explored a future where the universe expands forever, its fabric torn apart in a great unraveling. But what if that is not its destiny? What if the expansion we are currently witnessing is merely the universe in the middle of a great exhale, a phase that will eventually slow, pause, and then reverse into a long, slow, cosmic inhale? This is the vision of the Big Crunch, an end of fire, convergence, and a final, spectacular return to the beginning. To imagine this future, we must picture a sky that is the complete opposite of the one painted by dark energy's endless expansion. In the unfathomably distant future, a lone astronomer on a distant world might look through their telescope and notice something has changed. The distant galaxies, which for eons had been redshifted and fleeing, would no longer be red. Their light would now be shifted toward the blue end of the spectrum, the telltale sign that they were no longer moving away, but were now rushing back towards us. The great cosmic retreat would be over. The universe would have begun to contract. As the eons passed, this contraction would accelerate, and the night sky would begin to put on a breathtaking and terrible show. It would not grow darker and emptier, but brighter and more crowded. The points of light from approaching galaxies would grow in size and intensity, their blue shifted light making the darkness of space itself begin to glow with a faint, eerie luminescence. The universe would be shrinking, and every part of it would be rushing together in a great cosmic homecoming. This scenario of the Big Crunch was the leading theory for much of the 20th century, as it is the natural outcome of a universe governed by gravity. If the average density of all the matter and energy in the cosmos were above a certain critical value, then its collective gravitational pull would be strong enough to eventually act as a powerful brake on the expansion, slowing it to a halt and then pulling everything back together. As the collapse gained momentum, galaxies that were once separated by billions of light years would find themselves on a collision course. The universe would become a chaotic demolition derby of merging galaxies, their spiral arms tangling, their stars thrown into new orbits. The space between things would be shrinking, so collisions would become more and more common. As the universe continued to shrink, it would also get hotter. The cosmic microwave background radiation, the faint, cold afterglow of the Big Bang, would be compressed and energized, its temperature rising from a few degrees above absolute zero back up to thousands, and then millions of degrees. The universe would become a giant oven, so hot that the surfaces of stars would begin to boil away, and the planets orbiting them would be vaporized. Eventually, the background temperature would become hotter than the cores of the stars themselves, and they would be unable to shed their own heat. They would swell and explode, their matter dissolving into an ever denser, ever hotter primordial soup of particles. In its final moments, the universe would become a raging inferno of unimaginable temperature and density, all of space and time and matter rushing together, faster and faster, until everything was crushed back into the single, infinitely hot, infinitely dense point from which it all began, a gravitational singularity. This vision of the end has a powerful, poetic symmetry. It is a perfect, closing circle. The universe returning to the womb, the end becoming the beginning. It feels like a complete story, a grand narrative with a definitive and final conclusion. But if the universe could collapse back into a single, infinitesimal point, could that point truly be the end? Or could it instead be the seed for a new beginning? Could the end of one universe be the explosive birth of another? Think of a great forest that has been swept by a fire. For a time, all that remains is a landscape of black and ash, a scene of apparent devastation and finality. But if you return a few weeks later, you will see a miracle. From the nutrient-rich, fire-cleansed soil, tiny new green shoots will be emerging, reaching for the sunlight. Life, it seems, has a profound resilience, an innate ability to find a new beginning in the heart of an ending. Nature is full of these cycles of death and rebirth. The falling leaves of autumn become the fertile ground for spring. Why should the universe itself be any different? The idea of a big crunch, a fiery end where everything collapses into a single point, feels like a definitive finale. But some cosmological theories ask us to imagine that this point of infinite density is not a full stop, but a cosmic turning point, a moment of profound transformation where the universe, like a phoenix, is reborn from its own ashes. This is the heart of the Big Bounce hypothesis. To understand this, we must journey to the very edge of our knowledge, to the moment of the crunch itself. Here, the entire mass and energy of the universe is compressed into a space smaller than an atom. Under these extreme conditions, our current theories of physics, including Einstein's general relativity, break down. They give us nonsensical answers of infinite density and infinite temperature. This is what physicists call a singularity, and it is largely seen as a sign that our theory is incomplete. To see what might really happen, we need a new theory, one that can unite the world of the very large gravity and space-time with the world of the very small quantum mechanics. This undiscovered theory is often called quantum gravity, and while we do not have a complete version yet, we have some fascinating candidates. One of the most prominent is called loop quantum gravity. In this theory, the fabric of space-time is not a smooth, continuous sheet, as Einstein envisioned. Instead, it is made of discrete, indivisible units, tiny atoms or loops of space-time, on an incredibly small scale. Just as a picture on a screen is made of pixels, or a piece of cloth is woven from threads, space-time itself has a fundamental, granular structure. This has a profound implication for the Big Crunch. Because space-time is made of these finite chunks, it cannot be compressed to an infinitely small point. There is a minimum possible size, a maximum possible density that the universe can reach. As the universe collapses, it gets squeezed tighter and tighter, but when it reaches this fundamental limit, the quantum nature of space-time itself creates an immense repulsive force, a kind of cosmic rebound that pushes back with unimaginable power. The collapse halts and reverses in an instant, triggering a new, explosive expansion. The Big Crunch bounces and becomes a new Big Bang. This idea transforms our view of the cosmos from a single, one-off event into a potentially endless cycle of expansion and contraction. Our universe could be just one in an infinite series, a single breath in the eternal life of a cosmos that has no beginning and no end. It would mean that long before our Big Bang, another universe existed, with its own stars and galaxies, which collapsed and then bounced to create ours. And in the distant future, our own universe may collapse and bounce, giving birth to the next one in the chain. This vision is deeply comforting to some, as it removes the terror of a final, absolute end, replacing it with a sense of eternal process and boundless possibility. But these grand, fiery scenarios of ripping and crunching and bouncing are all dramatic and swift. Our current observations of the accelerating cosmos, however, suggest they may not be our most likely fate. The evidence today points toward another, different possibility, an ending that is far less theatrical, one that is colder, quieter, and much, much slower. Can you imagine a cold so absolute that the very dance of atoms slows to a near-perfect stillness? A darkness so profound and so complete that the last photon of light, the final, lonely traveller from a long-dead star, has long since completed its journey and found its rest. This is the landscape of the most likely, though perhaps the least dramatic, of all possible futures for our universe. It is an ending without a great tear in the fabric of space, an ending without a fiery collapse and rebirth. It is a destiny written not in a sudden, violent climax, but in the slow, patient, and inexorable language of thermodynamics. This is the future known as the Big Freeze, or more poetically, the heat death of the universe. It is a story of a universe that simply, over eons of unimaginable length, grows old, tired, and finally falls into a deep and eternal sleep. To visit this future, we must travel forward in time, past the lifespan of every star we see in the sky tonight, into an age of profound and peaceful twilight. Let us travel forward 100 billion years into the future. The accelerating expansion driven by dark energy has continued relentlessly, pushing most of the galaxies beyond our cosmic horizon, leaving our local group of galaxies as a single, large, gravitationally bound island called Milkomeda, formed from the merger of the Milky Way and Andromeda. Within this island galaxy, stars are still being born, but the great reservoirs of interstellar gas and dust are growing thin. The glory days of star formation are over. Now, let us leap forward again, to 1 trillion years from now. The last of the gas has been used up. No new stars are being born. The universe has run out of the raw materials for creation. The only lights in the sky are from the stars that already exist, and they are beginning, one by one, to die. The massive blue giants are long gone, having exploded as supernovae eons ago. The sun-like stars, like our own, have all shed their outer layers and become cold, fading white dwarfs. All that remains are the smallest, most frugal, and longest living stars in the cosmos, the dim, faint red dwarfs. For trillions upon trillions of years, these tiny, ember-like stars will be the only beacons of light in the ever-expanding darkness. They will sip their hydrogen fuel with incredible efficiency, shining with a feeble, crimson glow. But even they are not eternal. One by one, after lifespans of up to 100 trillion years, the last of these red dwarfs will finally exhaust its fuel and fade to black, leaving behind its own tiny, cold corpse. And with the extinguishing of that final, lonely star, the stelliferous era, the age of stars, will come to an end. The universe will be plunged into a darkness that will never again be broken by the light of a star. What is left is a cosmos that has become a vast, cold, and dilute graveyard, an era known as the degenerate era. Drifting silently in the near-perfect vacuum are the remnants of a brighter age. Countless black dwarfs, the final state of white dwarfs, cold neutron stars, and solitary black holes of all sizes. The distances between these objects are immense and growing with every passing moment due to the continued expansion. For a period of time, so long it defies all human intuition, this is the state of the universe. But even these degenerate husks may not be permanent. Some theories of physics, called grand unified theories, predict that protons themselves are not truly stable, and that over immense timescales, they will decay into lighter particles and radiation. If this is true, then over a period of 10 to the power of 40 years or more, even the dead stars, the black dwarfs and neutron stars, will slowly dissolve, their very substance evaporating away into a thin, cold mist of photons and neutrinos. The universe will become an almost empty void, populated only by stray particles and the last great holdouts against decay. The black holes. This final state is the logical conclusion of the second law of thermodynamics, the principle we first met in the embers of a simple campfire. It is the universe reaching a state of maximum entropy, a state of perfect, unchanging equilibrium. All usable energy has been spent, all matter has decayed, and all that is left is a thin, uniform sea of energy, spread out perfectly evenly across the vastness of space. There are no hot spots and no cold spots, no clumps of matter and no empty voids. Because there are no differences in temperature or density, no work can be done. Nothing can happen. Change itself will cease. This is not a violent end, but an end of utter exhaustion. It is the universe having finally reached a state of eternal, silent, and unchanging peace. And yet, even in this cold, dark, and seemingly final state, there are actors that play a game of time on scales that make even proton decay look swift. What becomes of the last sentinels of gravity, the black holes? We think of black holes as the ultimate prisons of the cosmos, objects of such immense gravity that nothing, not even light, can escape their grasp. They are the great devourers, the points of no return, symbols of permanence and eternity in a universe of constant change. We imagine them as eternal monuments to gravity's power, silently accumulating mass and growing ever larger as they drift through the cold darkness of the far future. But this vision of eternal permanence, like so many others, is an illusion. For even these cosmic titans, the most stable and massive objects to ever exist, are subject to the subtle and patient laws of quantum mechanics. And over timescales that are so vast, they render human language almost meaningless. Even the black holes will eventually wither away and disappear, giving a final, faint, and almost imperceptible sigh back into the void. Their slow demise is the final chapter in the story of our universe, the long goodbye of gravity itself. The key to this incredible process lies in one of the most beautiful and startling discoveries of modern physics. Hawking radiation, a concept developed by the physicist Stephen Hawking in the 1970s. He was able to show that, when the strange rules of quantum mechanics are applied to the edge of a black hole's event horizon, a surprising thing happens. Black holes are not completely black. They must glow, ever so faintly, with a thermal energy. The mechanism behind this is rooted in the bizarre nature of the quantum vacuum. We think of empty space as being truly empty, but in the quantum world, it is a bubbling, fizzing sea of activity. Pairs of virtual particles, a particle and its corresponding antiparticle, are constantly popping into existence from borrowed energy, only to collide and annihilate each other a fraction of a second later, paying back their energy debt. This happens everywhere, all the time. Hawking realized that if one of these particle-antiparticle pairs were to appear right at the very edge of a black hole's event horizon, it would be possible for one particle to fall into the black hole while the other one escapes out into space. From the perspective of a distant observer, it would look as though the black hole had just emitted a particle. Now, for the escaping particle to become a real, long-lived particle, it needs to take some energy from somewhere, and it takes that energy from the only place it can: the gravitational field of the black hole itself. According to Einstein's famous equation, E equals mc squared, energy and mass are two sides of the same coin. So, when the escaping particle carries energy away from the black hole, it is also carrying away a tiny, tiny fraction of the black hole's mass. The black hole gets ever so slightly smaller. Over an immense period of time, as this process repeats again and again, the black hole will slowly lose mass and evaporate. The process is, for any black hole of a significant size, unbelievably slow. A black hole with the mass of our Sun would take around 10 to the power of 67 years to evaporate completely. The supermassive black holes at the centers of galaxies, which can be billions of times more massive than the Sun, will endure for an almost unimaginable length of time. They will last for as long as 10 to the power of 100 years, a number known as a googol. This is a timescale so colossal that if you were to wait for the entire age of the current universe to pass, and then do that 1 billion, trillion, 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 trillion times over, you would still not be even a fraction of the way through the lifespan of a single large black hole. For nearly an eternity, they will be the kings of the dark, cold universe. But they are not eternal. They too will eventually shrink, and in their final moments, as they become very small, the evaporation process will accelerate, and they will disappear in a final, weak flash of light and energy. The discovery of Hawking radiation is a profound statement about the nature of reality. It shows that nothing, not even the most powerful and seemingly indestructible objects in the cosmos, is immune to the relentless march of time and decay. It is the universe's final whisper, the last, slow exhalation of entropy, playing out over a timescale that strains the very limits of our imagination. So, after the last star has died, after the last proton has decayed, and after the very last and largest black hole has evaporated into a final puff of radiation, what is left? Is it a true, final, and eternal nothingness? Or could there be one last surprise, a hidden flicker of possibility, a fundamental flaw in the very fabric of that final, empty void? Imagine, for a moment, that you are sitting in a perfectly still and quiet room, a space you have known your entire life, a place of complete stability and comfort. The floor is solid beneath you, the walls are steadfast. Now, imagine that without any warning, without a sound or a tremor, the floor beneath you is suddenly no longer the floor. It has, in an instant, transformed into something else entirely, something with new properties, new textures, and governed by entirely new rules of existence. This disorienting and instantaneous transformation is perhaps the closest we can come to understanding one of the strangest and most unsettling possibilities for the end of our universe, a scenario that arises not from the grand cosmic forces of gravity or expansion, but from the subtle, probabilistic weirdness of quantum mechanics. It is a cosmic wildcard known as vacuum decay, and it suggests that the very foundation of our reality may not be as stable as it seems. To understand this idea, we must first picture the vacuum of empty space not as a complete nothingness, but as a physical field that fills the entire universe, a bit like an ocean. This field, called the Higgs field, is what gives elementary particles their mass. And like any physical system, this field wants to rest in its lowest possible energy state, just as a ball will always roll to the bottom of a valley. The question is the valley our universe is currently resting in the absolute lowest valley there is? Or is it possible that our universe is in what physicists call a false vacuum? The best way to visualize this is to imagine a long, high shelf with a wide, deep bowl at the very end. But just before that final bowl, there is a much smaller, shallower dip in the shelf. A marble rolling along this shelf might come to rest in this small, shallow dip. It would be stable. As long as nothing disturbed it, it would stay there. But it would not be in its most stable possible state, which would be at the bottom of the deep bowl at the end. This small dip is the false vacuum. The deep bowl is the true vacuum. Our universe, according to this hypothesis, might be like that marble, resting peacefully in a state that feels stable, but which is not the ultimate ground state of reality. Now, in the classical world, the marble would need a significant push to get it out of the small dip and on its way to the deeper bowl. But in the quantum world, strange things are possible. There is a small but non-zero probability that the marble could, at any moment, spontaneously tunnel right through the energy barrier of the hill, separating it from the lower state. It could simply vanish from the shallow dip and reappear in the deeper bowl. According to the theory of vacuum decay, this could happen to our universe. At any random moment, in any random place, a small patch of the vacuum could spontaneously tunnel from our current false vacuum state into the true, lower energy vacuum. This event would create a tiny bubble of this new, true vacuum. And this bubble, once created, would begin to expand outwards in all directions at the speed of light. Inside, this bubble would be a new universe, a new reality. The laws of physics as we know them would no longer apply. The fundamental constants of nature that determine everything from the strength of gravity to the charge of an electron could be different. The very properties of the elementary particles that make up all matter could be radically altered. As this bubble of new reality expanded at the speed of light, it would be the ultimate agent of change. Everything it encountered, every particle, every planet, every star, every galaxy, would be instantly and seamlessly converted into this new state of being. This would be an end unlike any other we have considered. It would come without any warning whatsoever, because no signal or information can travel faster than the bubble's expanding wall. One moment, the universe would be as it is, and the next, it would be replaced by something utterly new and incomprehensibly alien. It would not be an annihilation into nothingness, but a complete and instantaneous phase transition, like water flash freezing into a strange new form of ice. It is the universe's ultimate reset button, a sudden and final shift in the very operating system of reality. All of these endings we have explored, from the slow, cold fade of the Big Freeze to the sudden reboot of vacuum decay, are governed by the dispassionate and impersonal laws of physics. But woven into the fabric of this particular universe, for this brief and fleeting moment in cosmic time, there exists something else, something that is aware of these laws. So we must ask, what is the role of the one thing in the universe that can look up at the stars and contemplate its own end? What is the fate of consciousness? There is an old philosophical question that asks, if a tree falls in a forest and there is no one around to hear it, does it make a sound? A physicist would say, yes, of course it does. The falling tree creates vibrations in the air, pressure waves that exist regardless of whether an eardrum is there to receive them. But a philosopher might pause and suggest that the sound itself, the subjective experience of hearing, is a product of consciousness, a translation of those physical waves into a perception. This gentle, ancient puzzle invites us to consider a much larger, more cosmic version of the same question. If a universe exists, with its billions of galaxies and its intricate physical laws, but there is no mind within it to witness its majesty, to measure its expansion, to feel awe at its beauty, is it still, in any meaningful sense, a universe? This question gently shifts our journey from the cold, hard physics of cosmic endings to the warm, subtle, and mysterious nature of our own awareness. Let us for a moment trace the incredible journey of that awareness. Imagine the earliest, simplest life on Earth, a single-celled organism drifting in a primordial sea. Its consciousness, if we can call it that, is merely a simple reaction to its environment, a movement towards light, a retreat from a chemical it dislikes. Now, let us move forward through the eons, through the branching tree of evolution, to the mind of a bird navigating by the Earth's magnetic field, or a wolf understanding the complex social dynamics of its pack. The awareness grows in complexity, in its ability to model the world. And then we arrive here, with the human mind, an instrument of such astonishing intricacy that it can not only model its immediate surroundings, but can also conceive of the distant past and the far future. It can invent mathematics to describe the motions of planets it has never visited, and it can build theories about the birth and the potential death of the entire cosmos. This journey, from a simple reaction to a profound contemplation, is one of the most extraordinary stories in the known universe. This special place we occupy, as observers, is addressed by a concept in cosmology known as the anthropic principle. The weak version of this principle, which is widely accepted, is quite simple. It states that the properties of the universe that we observe must be compatible with the existence of conscious, observing life, for the simple reason that if they were not, we would not be here to observe them. We find ourselves in a universe where the force of gravity is just weak enough, and the properties of the carbon atom are just right enough, to allow for stars to burn for billions of years, and for complex organic molecules to form. This can feel like a miraculous coincidence, but the anthropic principle suggests it is a kind of selection bias. We are alive in the kind of universe that allows for life, just as we find ourselves living on a planet that is not too hot and not too cold. From a psychological perspective, our fascination with the ultimate end of the universe is also a deep reflection of our own minds. Our brains are magnificent narrative machines. We are wired to see patterns, to seek out causality, and to structure our experiences into stories with a clear beginning, a compelling middle, and a satisfying end. We do this with our own lives, with the history of our societies, and so it is only natural that we project this same narrative structure onto the cosmos itself, searching for the final chapter. This deep-seated need for closure, for knowing how the story ends, is a fundamental part of what makes us human. Perhaps, then, the universe in and of itself is just an indifferent collection of particles and forces, without any inherent meaning or purpose. But by observing it, by studying it, by telling its story, consciousness imbues it with a meaning it would not otherwise have. We are, as the great astronomer Carl Sagan so beautifully put it, the universe's way of knowing itself. The silent, physical processes of the cosmos are transformed into a story of wonder, beauty, and discovery through the lens of our awareness. In this view, the end of all consciousness would be a truly profound kind of ending, for even if the physical universe were to persist in some cold, dark state, its story would be over. The witness would be gone. But if our particular form of consciousness, born of fragile biology and tied to this one small, temperate planet, is so vulnerable, could life itself, in some other, more resilient form, find a way to endure even the most extreme cosmic futures? We often think of life as a delicate and fragile flame, a fleeting anomaly that requires a very specific and nurturing set of conditions to exist. We picture a world like our own, bathed in the gentle warmth of a friendly star, with liquid water, a protective atmosphere, and an abundance of light. But the story of life on our own planet tells us that this is a profoundly limited view. Life is not a delicate flower. It is a tenacious and stubborn weed, capable of taking root in the most astonishing and seemingly inhospitable of places. On Earth, we have found life thriving where we once thought it was impossible. In the crushing pressures of the deepest ocean trenches, nourished not by sunlight but by the chemical energy from volcanic vents. In the boiling acidic water of hot springs, frozen solid inside Antarctic ice, and in environments so radioactive they would be instantly lethal to us. These remarkable organisms, known as extremophiles, are a profound testament to life's incredible ingenuity and its relentless drive to persist. They teach us that life is not so much a thing as it is a process, a masterful adaptation to whatever energy sources are available. And this raises a truly wondrous question. If life can find a way in the most extreme corners of our world, could it also find a way to survive in the most extreme eras of the universe's future? Let us travel forward in time once more, into the cold and dark degenerate era we visited earlier. The stars have all gone out. The universe is a dilute, ever-expanding graveyard of stellar remnants. The temperature is approaching absolute zero. From our warm-blooded, biologically biased perspective, this is a cosmos utterly hostile to life. But perhaps we are simply lacking in imagination. The physicist Freeman Dyson famously contemplated this very problem, and he speculated that life, or at least intelligence, could find a way to adapt and endure even in this bleakest of futures. His ideas hinged on a simple, elegant observation. Life is fundamentally a process of gathering, processing, and storing information, and this process requires energy. In a cold and dark universe, the primary challenge for any form of life would be the scarcity of energy. Therefore, any life that survived would have to become a master of energy conservation. Dyson realized that the key to this was to live slowly. An organism's rate of metabolism, its speed of thought and action, is directly tied to its body temperature. A warm, fast-moving creature, like a hummingbird, burns through energy at a tremendous rate. A cold-blooded reptile, on the other hand, lives a much slower, more energy-efficient existence. Future life in the cold universe would need to take this principle to its ultimate conclusion. To survive, these beings would have to be incredibly cold, their body temperatures only a fraction of a degree above the absolute zero of the background space. And as a result, their processes of life and thought would be unimaginably slow. A single, conscious thought might take millions, or even billions, of our years to complete. They would be beings of immense patience, living on timescales that would make the current age of the universe seem like a fleeting instant. They might enter long periods of hibernation, lasting for trillions of years, waiting for a rare opportunity to gather a scrap of energy, perhaps from the collision of two brown dwarfs, before processing their thoughts for another few billion years. The very substance of this life would also have to change. Our fragile, carbon-based chemistry, so dependent on liquid water and warmth, would be useless. Perhaps life would learn to build itself from more robust materials, becoming beings of plasma and magnetic fields, or intricate crystalline structures. Perhaps consciousness could exist in the complex gravitational dance of a binary system of neutron stars, sipping energy from its orbital mechanics. Life at the end of time would be a life of the mind, a slow, deep, and patient contemplation, a final flicker of awareness in the encroaching dark. Life, in its essence, is a struggle to create and maintain complex, ordered patterns of information against the relentless tide of entropy, which seeks to smooth everything out into featureless chaos. Perhaps this struggle is so fundamental, so deeply woven into the laws of nature, that it will find a way to continue in forms we can scarcely dream of, until the very last usable embers of energy in the universe are finally extinguished. All of our understanding of these possible futures, and indeed all of our science, is built upon the information we can gather and process now. But what is information itself, from a fundamental, physical perspective? And can it ever truly be destroyed? Think of a book that you love, its pages filled with a story that has moved you, characters you feel you know, ideas that have changed the way you see the world. Now, imagine that book is cast into a fire and burned to ash. The physical object, the paper and ink, is gone forever. But is the story it contained, the specific sequence of words and sentences that made it so special, truly and irretrievably lost? On the one hand, it seems so. The pattern has been destroyed. But on the other hand, a physicist might tell you that, in principle, if you could capture every single particle of ash and smoke and heat that was produced, and trace its trajectory perfectly, you could reconstruct the original state of the book. The information, they would say, is not destroyed, merely scrambled and dispersed in a way that makes it impossibly difficult for us to read. This simple image opens a door to one of the deepest and most profound principles in all of modern physics, the idea that information is a fundamental, physical quantity, and that, just like energy, it can never truly be lost. When a physicist talks about information, they do not just mean words or data stored on a computer. They mean a complete and precise description of the state of any physical system. Imagine a single atom floating in space. Its information is a complete list of its properties, its position, its momentum, its energy level, its quantum spin. The information of a gas in a room would be the precise state of every single molecule within it. This is not just a philosophical concept. It is a core tenet of quantum mechanics, our most fundamental theory of reality. This theory insists that the total amount of information in a closed system must be conserved. It can be rearranged, shuffled, or encrypted, but it can never be erased from the universe. This law of the conservation of information is as central to quantum physics as the conservation of energy is to all of physics. For a long time, however, there seemed to be one place in the universe that flagrantly violated this sacred law: a black hole. This puzzle is known as the black hole information paradox, and it has been one of the greatest challenges in theoretical physics for the last 50 years. According to Einstein's theory of general relativity, when a physical object, like our book, falls into a black hole, it passes the event horizon and is lost forever. The detailed information about the book, the precise arrangement of its atoms, is seemingly wiped from the universe, leaving behind only the black hole's total mass, spin, and charge. Then, as we discovered, black holes slowly evaporate over eons by emitting Hawking radiation. The problem is that this radiation appeared to be purely thermal, meaning it was completely random, like the hiss of static from a radio. It seemed to contain no information whatsoever about the specific things that had fallen into the black hole. So, when the black hole had finished evaporating, all of the unique, detailed information of everything that had ever formed it would be gone, erased from reality. This created a profound conflict. General relativity said information was destroyed, while quantum mechanics insisted it must be conserved. One of them had to be wrong. A possible, though truly mind-bending, solution to this paradox comes from an idea called the holographic principle. This principle suggests that all of the information needed to describe a three-dimensional volume of space is actually encoded on its two-dimensional boundary surface, just like a three-dimensional image from a hologram is encoded on a two-dimensional film. In the context of a black hole, this would mean that the information of our falling book is not lost inside the black hole's three-dimensional volume, but is instead imprinted and stored on the two-dimensional surface of its event horizon. Then, as the black hole evaporates, this information could be subtly and intricately encoded into the outgoing Hawking radiation, preserving it and returning it to the universe. If information is truly and fundamentally conserved, then the implications are staggering. It would mean that nothing is ever truly lost. The complete story of our universe, the precise state of every particle that made up every star, every planet, and every living being, is not erased by the passage of time, but is permanently woven into the fabric of the cosmos. The echo of our existence, the complete information of this very moment, might persist in some scrambled, encoded form forever. This brings us to the very nature of time itself. We perceive it as a flowing river, carrying moments away from us, losing them forever to the past. But is that perception the reality? We live our lives on what feels like a moving train, watching the landscape of the past recede behind us, while the unknown territory of the future rushes to meet us through the front window. Our entire experience is built upon this perception of forward motion, this relentless, flowing river of time that carries us from birth to death. The past is gone, a collection of memories, and the future is yet to be written, a realm of possibility. The only thing that feels truly real is the fleeting, razor-thin moment of the present, the now that is constantly becoming the past. But what if this deeply ingrained feeling, this most fundamental aspect of our reality, is a profound and beautiful illusion? What if the entire track upon which our train is travelling, the landscape of the past, the station of the present, and the destination of the future, already exists, complete and unchanging? This is the vision of the block universe, and it invites us to see time not as a river, but as a vast, frozen ocean. To grasp this idea, imagine a large, clear block of ice. Frozen within this block is a delicate and intricate pattern, perhaps a swirling three-dimensional sculpture of a branching tree. If we were to take a very thin sheet of light and pass it through the block from one end to the other, we would see a series of two-dimensional cross-sections of the tree. At one point, we might see the base of the trunk. As we move the slice of light forward, we would see the trunk split into branches, and then those branches into smaller twigs, and finally into delicate leaves. Each slice would represent a different moment, a different now. But the crucial point is that the entire tree, from its roots to its highest leaves, exists simultaneously and completely within the block of ice. Its beginning does not cease to exist when our slice of light has passed it, nor does its end wait to be created. The whole pattern is a single, unified, and timeless object. This is the essence of the block universe, or eternalism, a view of time that arises naturally from Einstein's theory of relativity. In this view, the universe is a four-dimensional block of space-time. Three of the dimensions are the space we know: length, width, and height. The fourth dimension is time. Every event that has ever happened, is happening, or ever will happen, has its own unique set of coordinates, its own specific location, within this four-dimensional block. The Big Bang is not a moment that is gone forever. It is the boundary of the block at one end. The birth of our solar system is a specific location within the block. This very moment, as you listen to these words, is another location. And the ultimate, final state of the universe, whether it be a cold, dark void or a fiery crunch, is simply the boundary of the block at the other end. Our consciousness, in this view, is the slice of light, illuminating one moment after another, giving us the powerful impression that time is flowing. The reason this view is so compelling to physicists is that Einstein's theory of relativity showed that the present moment is not absolute. If you and I are moving at very different speeds, we will have different perspectives on which events in the universe are happening now. There is no universal, privileged present moment that we all share. This suggests that the distinction we make between past, present, and future is not a fundamental feature of reality, but a feature of our perception of it. The implications of this idea are profoundly comforting. If the block universe is a true picture of reality, then no moment is ever truly lost. The past is not a vanished memory. It is a real and permanent landscape within the block of space-time. Every moment of joy you have ever experienced, every cherished conversation, every beautiful sunset you have witnessed, is not gone. These moments have not ceased to exist. They are forever etched into the fabric of reality, as real and as present in their own coordinates as this moment is in yours. It suggests that our lives are not a fleeting flicker of light, but a complete and finished pattern, a permanent part of the cosmic sculpture. And with all these vast possibilities laid out before us, from a universe that rips apart to one that is reborn, to a reality where all of time exists at once, what does it truly mean to ask, how will it end? Perhaps the question itself is framed by our limited, human perspective, which longs for a simple, linear story. We search, with our telescopes and our equations, for a definitive final chapter to the story of the universe. We yearn to know which of these grand scenarios will come to pass, to have the certainty of a final page that resolves all the plot lines and tells us what it all meant. But what if the universe is not a story? What if it is not a book to be read from beginning to end, but something more like a poem or a piece of music? Imagine you are listening to a beautiful symphony. It has a beginning, a middle, and an end, but its value and its beauty do not reside solely in its final, fading chord. The beauty is in the entire composition. The quiet opening notes, the build-up of tension in the middle, the soaring melodies, the quiet passages, the interplay of every instrument and every moment from start to finish. To focus only on the final note would be to miss the entire point of the music. The journey is the experience. Perhaps our universe is the same. Perhaps its meaning is not to be found in its ultimate destination, but in the breathtaking complexity and beauty of its entire, unfolding existence. This shift in perspective brings us to the very heart of what science is and what it is not. As we saw earlier, our human minds have a powerful narrative bias. We are natural storytellers, and we instinctively try to fit the vast impersonal workings of the cosmos into the familiar, comfortable structure of a tale with a beginning, a middle, and an end. But science, at its best, is a process of letting go of these biases and trying to see the universe on its own terms. Science does not provide absolute truth or final, unshakable certainty. What it provides are models, maps that represent our best current understanding of reality based on the available evidence. The scenarios we have explored, the big freeze, the big rip, the big crunch, vacuum decay, are our best, most sophisticated models for the future, but they are still just models. They are provisional, subject to change and refinement as we gather new data and develop new ideas. They are the frontiers of our knowledge. The edge of the map where the territory is still marked here be dragons. A key principle in the philosophy of science, championed by the philosopher Karl Popper, is the idea of falsifiability. This principle states that for a theory to be considered scientific, it must be testable. There must be some conceivable observation or experiment that could prove the theory wrong. It is this very vulnerability, this openness to being proven false, that gives science its strength and its integrity. A belief that cannot be falsified, a statement that can accommodate any and all outcomes, is not science. It is a matter of faith. The theories about the end of the universe are scientific precisely because they are falsifiable. They make concrete predictions. For example, the Big Rip scenario predicts a very specific behavior for dark energy, something that future, more powerful telescopes might be able to measure. If those measurements show that dark energy does not behave in that way, then the Big Rip model will be falsified, and we will move on to other ideas. This is not a failure of science. It is the very process of science working as it should, a slow and steady refinement of our understanding, a gradual peeling back of the layers of the cosmic onion. The true value, then, is not in having a single, final answer right now. The value is in the quest itself, the magnificent, multi-generational human endeavor of looking up at the sky and wondering, of building tools to see farther, of creating mathematics to understand deeper, is one of the most beautiful and meaningful things we do. The act of asking the question is what gives our existence a profound context, regardless of what the ultimate answer may be. The mystery is not a problem that needs to be solved, but a gift that invites us into a deeper relationship with the cosmos. So, after this long journey through dying stars, expanding space, and the very nature of time, where do we find ourselves? We find ourselves back in the quiet of the present moment, with the cosmic symphony still playing all around us. A cherry blossom in Japan is cherished not for its longevity, but for its breathtaking and transient beauty. Its pale pink petals are a celebrated symbol of spring, but their appearance is fleeting, lasting for only a week or two before they are scattered by the wind like a soft, fragrant snow. The blossom is so deeply beautiful to us, not in spite of its short life, but precisely because of it. Its impermanence makes the moment of its existence infinitely more precious. It is a gentle reminder that life's most beautiful moments are often its most fleeting, and it is their finitude that urges us to pay attention, to be present, to appreciate them fully before they are gone. This wisdom, found in a simple flower, can be a comforting guide as we contemplate the grand, cosmic scales of time and the eventual end of all things. For if we look closely, we find this same poignant beauty woven into the very fabric of our lives, and perhaps into the fabric of the universe itself. Let us bring our attention away from the far-flung future and back to this very moment. Perhaps you are holding a warm cup of tea in your hands. Feel its gentle heat seeping into your palms. Watch the delicate wisp of steam rising from its surface, curling and dancing in the air for a moment, before disappearing completely. It is a small, perfect, and utterly temporary experience. It is here now, and in a moment, it will be gone. The tea will cool, the steam will vanish, the moment will pass. And yet, its value is found right here, in its present, fleeting warmth. This is the nature of our existence. We are creatures of finite time, living lives that are, from a cosmic perspective, as brief and as beautiful as the life of a cherry blossom. The eventual, distant end of the universe can feel like a cold and abstract concept, but it is a perfect mirror of a much more intimate and immediate truth, that our own time, too, will come to an end. And this knowledge, which could be a source of fear, can instead be the very thing that gives our lives their shape, their urgency, and their profound meaning. From the perspective of evolutionary psychology, our acute awareness of our own mortality is one of the most powerful forces shaping human civilization. The knowledge that our time is limited is a tremendous motivator. It is the engine that drives us to create things that will outlast us, to paint masterpieces, to compose symphonies, to build great structures. It is the impulse behind our desire to form deep and lasting bonds with one another, to love, to teach, and to share our wisdom with the next generation. All of these endeavors, art, science, family, community, are our noble and beautiful attempts to create order, meaning, and legacy, to push back against our own personal entropy and leave an imprint on the world that will endure, for a time, after we are gone. One could even imagine that a truly infinite life, an existence without end, might paradoxically become a meaningless one. If you had an eternity to do everything, what would be the urgency to do anything? What would be the motivation to choose one path over another, to cherish one moment above the rest? A story with no end is a story with no plot. It is the finitude of our lives that gives them their narrative arc, that forces us to make choices, to decide what is truly important, and to savor the preciousness of the present. Perhaps the universe is no different. Perhaps its own finite existence, however impossibly long it may be, is precisely what makes it so magnificent. The fact that the stars will one day die, that the galaxies will one day fade, makes the starlight we see in the sky tonight all the more wondrous. We cherish the light because we know it cannot shine forever. The cosmos is a grand, cosmic cherry blossom, and we are living in the perfect, fleeting moment of its bloom. Knowing all of this, knowing that everything, from a wisp of steam to the mightiest star, is in a constant state of beautiful and temporary flux, how then do we live? The universe, with its silent, swirling galaxies and its deep, immutable laws, asks us a profound and open-ended question simply by existing. And our lives, in all their brevity and with all their capacity for love, curiosity, and wonder, are our answers. We answer with every work of art we create, with every scientific discovery we make, with every act of kindness we share, and with every moment we pause to simply appreciate the mystery of it all. All of human history, with its soaring triumphs and its deep sorrows, its brilliant insights and its foolish mistakes, can be seen as a single, brief, and beautiful thought in the mind of the cosmos. A fleeting but powerful flicker of awareness that, for a short time, tried to understand itself and the great whole to which it belongs. We have seen that science is not a book of final answers, but a continuous and humble process of asking better and better questions. The theories about the ultimate fate of the universe are the very edge of that process, the current frontier of our questioning. They represent the furthest limits of our collective human imagination, guided by mathematics and observation. But the true spirit of this endeavor is not about finding a final, dogmatic answer. It is about nurturing the very thing that drives the questions in the first place. Our innate and beautiful sense of curiosity. Curiosity is the engine of the human spirit. It is the force that led our distant ancestors to look up at the patterns of the stars and wonder what they were. It is the spark that drove generations of thinkers to build the tools and the theories that have allowed us to glimpse the universe's 14 billion year history. This desire to know, to understand, to see what lies beyond the next hill or the most distant star is not a trivial pastime. It is one of the most noble and essential parts of who we are. The specific question of what happens in the end is simply the ultimate expression of this deep-seated curiosity, the most fundamental what-if we can possibly ask. So perhaps the most peaceful and profound way to live with this grand cosmic question is to accept that we may never have the definitive answer, and to realize that maybe that is okay. Maybe the point is not to arrive at a final destination and close the book. Maybe the purpose is to simply travel through our lives with an open and a wondering heart. The mystery is not a flaw in our understanding. It is a gift. It is a vast, open canvas that invites our contemplation, our creativity, and our awe. It ensures that there will always be something more to learn, always something more to wonder about. It keeps us humble by constantly reminding us of the sheer scale of all that we do not yet know. To live in this way is to find peace, not in certainty, but in the beauty of the question itself. Our lives are not about finding the single correct answer to the universe's question, but about how beautifully and how fully we can live that question while we are here. The universe is vast, and its future is uncertain. But as we draw our journey of cosmic exploration toward its gentle close, we can turn our attention from the great, external universe to the one universe whose fate we can influence, the one whose landscape we can be certain of. The universe we hold within us. Close your eyes, if you feel comfortable doing so. Let the outside world, with all its light and motion, gently fade away and bring your awareness inward. Feel the slow, steady, and quiet rhythm of your own breathing. Feel the gentle rise of your chest as you inhale and the soft release as you exhale. This simple, effortless rhythm is the anchor of a universe of immense and breathtaking complexity, a cosmos of biology and consciousness that you hold entirely within you. While we have spent our journey together looking outwards to the furthest reaches of space and time, for these final few moments, let us travel inward, into an equally wondrous and mysterious domain. Here, within the quiet sanctuary of your own being, you can find a reflection of the entire cosmic story, a personal universe that is yours and yours alone. Imagine, for a moment, the vast network of your own mind. Your brain contains approximately 86 billion neurons, a number that is astonishingly close to the estimated number of stars in our Milky Way galaxy. Each of these neurons is a living cell, a tiny spark of awareness, and each one is connected to thousands of others, forming a web of pathways and connections that is more complex than any structure we have ever discovered in the universe. There are more potential connections between the neurons in your brain than there are stars in the known cosmos. When you have a thought, or a memory, or a feeling, it is not happening in one single place. It is a storm of electrochemical energy, a pattern of light and information flashing across this immense neural galaxy. A memory of a childhood home is not a single image, but a whole constellation of neurons firing in a specific, beautiful sequence, a pattern that has been encoded through your lived experience. Your mind is its own space-time, a place where you can travel effortlessly. With a single thought, you can journey back decades into the past, revisiting a cherished memory with vivid, sensory detail. And in the next moment, you can launch yourself into the future, imagining a day that has not yet happened, making plans, and exploring possibilities. This ability to navigate a personal timeline, to hold the past, present, and future together in our awareness, is one of the most profound aspects of our inner universe. And this entire, intricate cosmos is engaged in a constant, beautiful struggle to create order from chaos. Your senses are, at this very moment, being flooded with an overwhelming stream of raw, chaotic data. Sounds, temperatures, pressures, scents. Your mind, like a patient and masterful artist, takes this chaotic input and effortlessly weaves it into a coherent and meaningful story, the story you call your reality. Just as life itself creates ordered complexity in the face of universal entropy, your consciousness is a magnificent engine for creating personal meaning from random sensation. It is the calm, organizing center of your own existence. The grand dramas of the cosmos that we have explored, creation and dissolution, expansion and connection, the interplay of light and darkness, are not just abstract external events. They are mirrored within the very structure of your own conscious experience. By finding a sense of peace and stillness within this internal universe, by simply resting in the quiet rhythm of your own breath, you can touch a sense of the eternal that is not dependent on the fate of the most distant stars. And so, as we come to the end of our long and winding journey together, we travel back from the edge of time and from the depths of our own inner space to arrive in the quiet of this very moment with one final thought to carry with you into your dreams. After traveling to the far, cold edges of the future, after witnessing the birth and death of stars and the very unraveling of time, we have arrived at the only place in the entire cosmos that truly exists for us. Here and now. Feel the gentle weight of the blanket over you, a soft and comforting gravity all your own. Notice the feeling of the pillow beneath your head, supporting you without any effort. And return, once more, to the simple, steady rhythm of your own breathing, the quiet, reassuring anchor that has been with you through every moment of your life. This present moment, this simple act of resting, is the final destination of our entire journey. It is the quiet harbour we have been seeking all along, a place of perfect peace that is always available to you. We began our story tonight with the simple, familiar image of a dying campfire, its last embers glowing like a miniature galaxy before fading into ash. In that small, quiet ending, we found a reflection of entropy, the great, universal law that gently guides all things from order to disorder, the silent arrow of time. We journeyed from that small fire to the great fire in our sky, our sun, and we saw its own distant, future sunset, a slow and graceful expansion into a red giant before it, too, finds its rest as a cold, white dwarf. We witnessed the far more spectacular endings of the universe's true titans, the massive stars that die in supernova explosions, forging the heavy elements in their fiery hearts and scattering them across space to seed the next generation of stars, planets, and eventually, life. We remembered, literally made of stardust. From there, we zoomed out further, to the grand cosmic tug-of-war that dictates the fate of everything. We saw how the universe is held together by the invisible web of gravity and dark matter, while at the same time it is being pushed apart by the even more mysterious force of dark energy. We explored the possible outcomes of this battle. The violent, unraveling Big Rip, the fiery, cyclical Big Crunch and Big Bounce, and the most likely scenario, the The slow, quiet, and peaceful fade into a big freeze, a final heat death, where the universe reaches a state of eternal, unchanging stillness. We even considered the stranger possibilities, the quantum wildcards of vacuum decay, and the long, slow goodbye of black holes evaporating over a Google years. We questioned the very nature of time, of information, and of our own consciousness as the universe's sole witness. And now, after all of that, we have returned. We have come home. The universe will, in some way, on some timescale that is far beyond our own, come to an end. But that knowledge does not need to be a source of fear or sadness. It can instead be a gentle and profound reminder to cherish the warmth, the light, the connection, and the consciousness of this present moment. For this moment is a miracle. The entire, vast, 14 billion year history of the cosmos, the long chain of stellar births and deaths, the slow and patient coalescing of matter into our galaxy, our sun, and our Earth, has conspired to create this one perfect, quiet moment of rest for you. You are not separate from the universe. You are a rare, precious, and beautiful flowering of it. You are the cosmos made aware. And with that gentle thought, let this be a vessel to carry you into a deep and peaceful sleep. Thank you for joining me on this journey to the edge of time. If you have found a moment of peace or wonder here tonight, I would be so grateful if you would like this video and subscribe to the channel to help other souls find this quiet corner of the cosmos to rest in. I wish you the very deepest peace and the sweetest of dreams.